Okay, in this video we're going to talk about electrophilic aromatic substitution and then a specific kind of EAS, that being halogenation. In fact, the next several videos are going to be devoted to looking at different types of electrophilic aromatic substitution. Now the good news is all of these reactions are fairly similar, and so once you get the mechanism down for one, you should understand it for all of them. We've talked several times about how stable benzene is and how much less reactive it is compared to typical alkenes. And so we know that typical alkenes will undergo addition reactions with something like Br2, but benzene won't do that. Now we can get benzene to react with bromine if we include iron. Now, instead of getting an addition reaction where the bromine adds to the double bonds, we get a substitution reaction where the bromine replaces one of the hydrogens and the benzene retains its aromaticity. This is an example of electrophilic aromatic substitution, and so we'll spend the next couple of videos talking about these types of reactions. So all of these reactions down here are examples of electrophilic aromatic substitution. In all of these reactions, a hydrogen atom is replaced by an electrophile. The ring is acting as a nucleophile, but at the end of the reaction, the aromaticity of the ring is preserved in all of these reactions. And so in this video, we're going to talk about halogenation, so substituting a hydrogen for a bromine or a chlorine. Then in the next couple of videos, we'll talk about these other reactions. So when we learned about bromination of alkenes last semester, the bromine acts as an electrophile, the alkene acts as a nucleophile. So bromine can act as an electrophile, but it's not strong enough to attack a benzene ring. And so by including iron in the reaction mixture, we're going to make iron 3 bromide, and this is going to act as a Lewis acid catalyst to make Br2 a strong enough electrophile. So let's see how that works. So we have this iron 3 bromide, and it's going to undergo a Lewis acid base reaction with the Br2. So the FeBr3 is going to act as a Lewis acid, an electron pair acceptor, and the Br2 is going to act as a Lewis base, an electron pair donor. And when that happens, we end up with this complex where now that we have this positive charge on the bromine end of things, this is a much more potent electrophile than just Br2 by itself. And it's a strong enough electrophile that it can in fact react with benzene. Okay, so let's see what the mechanism for this reaction looks like. And this is going to be similar to the other EAS reactions that we're going to look at in the next couple of videos too. So in the first step, our complex, and in the other reactions is going to be some other electrophile, is going to act like an electrophile. The bromine is always going to act as a nucleophile, and so one of the pi bonds from the benzene ring, the nucleophile, is going to attack, in this case, the bromine. They're drawing in the hydrogen here because it's this hydrogen that we're going to be substituting for the bromine eventually. So in all of these EAS reactions, we're going to make what's called a sigma complex, where we have a carbocation that's part of this ring. And it's an allylic carbocation, so we always want to draw these resonance structures so we can show the carbocation being moved around the ring. Now this isn't aromatic anymore, right? We only have 4 pi electrons. That's not a Huckel number. So it does require a fair amount of energy in order to get this reaction to go, because at least temporarily, the benzene ring loses its aromaticity. Now, due to resonance, this carbocation is stabilized a little bit, but not nearly as much as the aromatic benzene that we started with. So the first step is always this nucleophilic attack to make the sigma complex. And then the second step is always a proton transfer. So the complex minus the bromine that we lost in the first step will steal this proton to give us the final product. And then that produces, this bromine leaves with the hydrogen that it's stealing, and then we reproduce our FeBr3, the catalyst. And we were saying that this acts as a Lewis acid catalyst, so we always have to regenerate the catalyst at the end of the reaction. And then the bromine has replaced that one hydrogen, and you can see the benzene has regained its aromaticity. So that's why we get substitution reactions, because the bromine can remain aromatic. If we'd had an addition reaction, that wouldn't have been the case. Okay, so there are a couple things here when we're looking at the reaction energy diagram. So the first thing we note is that there are two steps in the reaction mechanism, and so we should see two barriers in our reaction energy diagram. Also, we notice that the transition state is very high, right? And even the sigma complex, the intermediate, is very high in energy relative to the starting benzene compound, right? Even though the sigma complex was resonance stabilized, it had lost its aromaticity. So we have to put in a ton of energy to get this reaction to go, and the intermediate is relatively high in energy. And then you can also see the difference in energy between the product that we would have if we'd undergone addition versus substitution, where we just replaced a hydrogen with a bromine. The addition product, because it loses aromaticity, right, it's much less stable. And so that's why we get electrophilic aromatic substitution, and we're not generally going to see addition to a benzene ring, where we'd have to lose the aromaticity. All right, this is just a note on the catalyst. FeBr3 is not the only thing we can use. Aluminum bromide also works as a good catalyst, and the mechanism would be identical to the previous one. Essentially, just wherever you see the iron, replace it with an aluminum. Okay, so we've been looking so far at bromination. Chlorination is possible, only in this case, instead of using Br2 and AlBr3, we're going to use Cl2 and AlCl3. It turns out that the EAS really only works well with chlorine and bromine. Fluorine is too violently reactive to be practical, and then iodination is generally so slow to make it not very practical. If we look at the chlorination mechanism, it's identical to the bromination mechanism. The only difference is, in this case, they're using AlCl3 instead of FeCl3. But otherwise, it's identical, just replacing the chlorines with bromines. We first have nucleophilic attack, we make the sigma complex, and we end with a proton transfer. And in general, we're going to see that the mechanism for all of these EAS reactions is basically the same. We have some kind of nucleophile. We start off with the pair of the pi electrons undergoing nucleophilic attack on the electric file. We're always going to make a sigma complex, and we're always going to end with a proton transfer.